So I think we can start. Welcome back to the next session about modeling and simulation. It will start with a keynote presentation about simulation of switching devices on the example of a circuit breaker, the pros, the cons, and the way ahead. It will be held by Professor Nordborg from the University of Applied Sciences in Rapperswil, Switzerland. And we are very happy to have him for this topic, since he has a wide experience based on three important columns. First, industrial research with ABB on hardware, multi-physics consultant with CAD/FEM ANSYS software, and finally, professor of physics, focus on modeling and simulations, including arc simulations, research-wise. So a unique constellation, and we are curious to listen to you. Please go ahead.
Okay, thank you very much, Hans, for the introduction, and very welcome to this presentation. Perhaps a short clarification. I thought I had left the mergers and acquisitions behind me when I left the private sector, but apparently they also happen in the academic world, and I didn't change my office, but the organization around me changed. So we are now the Eastern Switzerland University of Applied Sciences. And of course, I'm very happy to be able to give this presentation in a virtual form this time, but that's also, I think, a very new and exciting development that we are currently experiencing. I would like to start by acknowledging my collaborators. There is some of you might know the joke about the 3 stages in the life of a professor or a researcher. The first stage, when you start out, you do all the research and someone else talks about it. Then you reach the second stage where you do the research and actually get to talk about it yourself. The third stage, obviously, is that someone else does the work and you still get to talk about it. And then the fourth state is that when nobody does any work and you still get invited to talk. I hope I haven't reached the fourth stage yet, but I'm definitely for this work in the third state and or the third stage. And the collaborators are Roman Fuchs, who will later be giving a presentation in this session. He recently finished his PhD at the ETH, and Mario Mürmann, who has unfortunately left us, but who has also been an important collaborator on this work. So what I would like to talk about is numerical simulations of electrical arcs, and to give a background, I'm a physicist. I did my PhD in some theoretical physics. I worked a lot on simulations. In those days, I worked on simulations of superconductors, high temperature superconductors, and I've always been fascinated by the topic. Therefore, when I joined ABB, I also started to get involved quite heavily in numerical simulations of various kinds. And thus I can say it has been a very exciting time, because since for the last 20 years, I joined ABB in the year 2000, there has of course been an enormous development in the simulation, in numerical simulations for product development, driven by better algorithms, better computers, faster computers, and better software tools. All these 3 have benefited or contributed to enormous advancement or advances in the field. And today, I think we should, it's fair to say that for many applications in the industry, there are lots of commercial tools available. There are also quite a number of public domain tools that exist. And the state-of-the-art line has been moving, just to give sort of a management-like plot. Management plots typically don't have any scales or numbers on the axis. It is clear that we're well past the beginning on if we are somewhere on an S-curve with numerical simulation. For most applications, we're probably up here where you can say the most important processes in many areas, such as structural mechanics, fluid dynamics, electromagnetics, can now be handled reasonably well with these simulation tools. But there is a phenomenon in the software industry, and since I spent 2 years working with CAD/FEM, being like a partner of ANSYS, I got to experience this firsthand. Software is typically developed this way, that you say there are, for each new release, you have an infinitely long list of requests collected from customers, and you have a finite number of programmers who are supposed to implement these requests. And what happens is, of course, that you make you prioritize these requests, and you typically pick the ones that can make many customers happy with as little code as possible. And unfortunately, numerical simulations of electrical arcs do not fall into this category, which means that I think if we compare to most other simulation technologies, we are a bit lagging behind. I think it's fair to say that simulations of electrical arcs, of arcing phenomena in product development, are not yet state of the art. It's not, they don't have the same maturity like finite element simulations or structural mechanics, for example. Why? Well, there are two threats, and this is something that has annoyed me for many years. I mean, one of the problems we cannot really solve, it involves hard work. It's the fact that it's very difficult from a physical standpoint. Well, that's the way it is. The other problem is that the simulation tools have not really been up to the job, and that's of course a problem, because if a physics is very difficult, it means that you have to run a lot of simulations. You have to do a lot of trial and error. You have to run many simulations to test different parameters, to test different settings, to try different models, to see what actually works. But if each and every simulation takes many days to finish, it's very difficult to do this in a systematic fashion. I personally believe that it would have been smarter to invest more effort in improving the simulation algorithms many years ago already, but I think there has been quite a lot of progress done anyway. So why arc simulations? I realized the next speaker is Professor Lindmeyer, and I must confess I borrowed this picture from a presentation he gave at ABB many years ago. I hope he doesn't mind. So as you know, I don't have to tell you this. Currents are typically still interrupted by the separation of two contacts. There are other ways around, but I think the contact separation approach will still be used. And of course, that means that we ignite an electrical arc in most cases. And now it's the question how to interrupt that. It would, of course, be very nice to have some device that has zero resistance until we reach current zero, and then has infinite resistance after current zero. If we had such a device, we could, of course, interrupt basically anything. Even if you don't have a current zero, if you don't have a zero crossing, you could still tweak the device somehow, introducing an artificial current zero, or, well, if arcing resistance would be infinite, you wouldn't even have to do that. Anyway, so that is what we would like to have. Unfortunately, such a beast does not exist. So we have to think about some approximate realization of that. And the approximate realization is, of course, an electrical arc, because it has a fairly high conductivity as long as there is significant current flowing through this arc. And once it starts cooling off, the resistance increases quite strongly. Of course, as many of you know, there is a very simple and very useful way of describing such an arc, which is called the Casimir equation, which is a dynamic equation describing the arc resistance. It's very simple, and it shows it basically only contains two parameters. One is the power dissipated by the arc. So U times I is, of course, the electrical power in the arc, the heating power from the current, and divided by the cooling power. And then there's a time constant. And if the electrical power is smaller than the cooling power, then the resistance of the arc increases exponentially with the times characteristic timescale tau. This is a very useful model. You can introduce that into circuits and couple this to circuits and see what happens. However, the problem is, of course, that we don't know these parameters. And of course, it's also not a perfect model. You can do more advanced integral models for electrical arcs, of course, but still the problem is you don't really know what the parameters are. And the idea is, of course, that if we do a detailed arc simulation, simulating all the physics, basically from first principles, we should be able to determine how the arc resistance depends on the current and other factors, such as geometry, the composition of a gas, etc. Why is this a bit challenging? It's challenging because arcs are complex phenomena. We have two electrodes. We have an arcing column with a very hot plasma inside. Of course, the arcing column interacts with the electrodes. Then, because it's so hot, most of the radiation or most of the energy lost by the arc is lost through radiation. But of course, there's also significant cooling because of gas dynamics. Then, of course, we have an electromagnetic field around the whole thing that, especially for high current arcs, leads to pinch effect that actually keeps the thing together. So there are lots of things to simulate. If you look at the different parts of this arc, one part is the fluid dynamics problem in itself is very tough because we are really talking about high temperatures. The core of arc can be like 20 to 30,000 Kelvin. So we have huge temperature differences, huge pressure gradients. Of course, the whole thing is very turbulent. Then, because of high temperatures, everything will dissociate. The components of a gas, of a plasma. Well, you start with some gas, and as soon as it starts to dissociate, you will get a plasma with many species. And then there is the radiation transfer, which also has to be solved as a separate problem, and you have to have a quite detailed modeling of that. Then the electromagnetic field is kind of tricky for this, well, for one reason, which is it's partly due to the way electromagnetic algorithms are being written, because most algorithms for the simulation of electromagnetic fields, they start by dividing the world into conductors and insulators. Then they use one algorithm or one formulation for simulating the electrical current in the conductors and another formulation for the insulator. That approach doesn't work very well for electrical arcs because we have a continuous drop of electrical conductivity. The electrical conductivity is high inside the arc, and then it drops continuously to almost zero outside the arc. So that is a bit of a challenge. Secondly, we also have the problem that, well, depending on the situation, if we have ferromagnetic materials, such as in low voltage breakers where we have splitter plates, etc., then that in itself is quite a tough problem. Then, of course, you have to couple electromagnetic fields and fluid dynamic simulations, which is, depending on which tools you use, can be very difficult or, well, more or less difficult. And then, of course, we have the boundary conditions that the arc actually interacts with the electrodes. And I think it's perfect that the next presentation by Professor Lindmeyer will talk about arc roots and how to model those. I will not say too much about it in my presentation. Compressible flow dynamics. In principle, it is known how to do it. The equations are a bit challenging. But the idea is simple. You solve transport equations for the mass, for the momentum, and the energy of the arc. Typically, the implementation is based on with finite volume, the finite volume scheme. There are very good reasons for doing that. And you need, in order to be able to use these equations, of course, we need material properties. We need to understand how does the pressure or the density depend on pressure and temperature, etc. We need the electrical conductivity, and you need radiation. I've color-coded the terms here. So what is actually new if you want to do an arc simulation is there is a Lorentz force in the momentum equation that gives you a force on the plasma. And then, of course, there's ohmic heating in the energy equation. And there is a significant radiation, energy loss through radiation. One issue which I alluded to previously is, of course, that we have to simulate this thing, and we need material properties. And due to the high temperatures, here are, for example, the specific heat of air as it is implemented, and we see clear peaks in the specific heat. The reason is, of course, that the whole plasma, when molecules dissociate, there is a certain latent heat that is related to this dissociation, and that shows up as peaks. So these material properties have to be implemented, and they have to be implemented very consistently. Then another topic is turbulence modeling, and I think this is something where there's clearly a lot of work to be done. There are few, I think, systematic studies of turbulence models for electrical arcs. I think there are very good reasons for this, because you have many unknowns, and I'm a strong believer in that you should not simulate things if you can't measure something. I mean, it's pointless to try to simulate something if you don't have good experimental data. And I think the challenge here is really to find experiments where you can really measure turbulent effects, and you simply need very good and very detailed data for doing that. So if someone has such data, I would be delighted to get in touch and talk about it, because I think we have a framework for simulating that. Radiation transfer it's a nasty equation, because radiation transfers, of course, if you model the irradiation in or the spectral radiance in a gas, you have to do this in every point and for every direction. So there is, in every point in space, you need to solve an equation for every direction, which you could write, for example, using two angles or a vector S. And in addition to that, all properties of a radiation are frequency dependent, meaning that, for example, the absorption coefficient in the plasma is frequency dependent, and it's not mildly frequency dependent. These strong peaks in the absorption are, of course, related to atomic energy levels or molecular atomic energy levels, where you have very strong absorption, and you see there are peaks which are 6-7 orders of magnitude higher than the background. Here is some sort of averaging is necessary, and there are some tricks that you can use. We solve this problem by renormalizing the peaks, and I think in my paper that I submitted, you can find some of the references to that. The electromagnetic field simulation is also kind of tricky. Well, the full set of Maxwell equations are fairly well known. The only difference you see if you have a plasma is that you have the current also have a convective part that is related to the velocity of a flow and the B field. You can typically we can assume the conductivity to be sufficiently large. This is actually the solution to the problem I alluded to previously. You simply assume that also the cold gas has some conductivity, and if you choose that conductivity to be small enough, you don't have a problem. Then you can ignore the displacement current, and you typically solve this equation by introducing the electromagnetic potential, so the scalar electric potential and the magnetic vector potential. Doing so, you still end up with a fairly nasty equation. This would be an equivalent formulation to what we had before. It is a transient equation for the electromagnetic potential. It has a diffusive part and it has a convective part. However, in most cases, and you can simply look at the scales, this is the dominant part. And then you can solve it as a magnetostatic problem. You can also, and of course, if then the magnetic permeability is if you don't have any ferromagnetic materials, you can actually solve then the magnetic problem using a finite volume method. Otherwise, you probably need to use finite element methods. Arc routes and ablations. We have implemented fairly standard models into those. I also gave references in the paper I've submitted. Basically, the effect is you need to have a voltage drop at the arc routes. Depending on the application, you need to model the contact erosion, so you create metal vapor at the arc routes. And of course, they're necessary or crucial for determining how the arc is moving. In some applications, for example, typically in high voltage breakers, but also in low voltage breakers, you need to implement wall ablation so that you get the appropriate pressure buildup. Our feeling is that this is all physics that happens on very short length scale. So ideally, it should be implemented as interface condition 2-dimensionally. And here, I mean, we haven't done too much here for the simple reason that we didn't have any experimental data needed to do so. So if anyone would be interested in collaborating with us, and we would be more than happy to improve our arc route models. The numerical challenge is, and I think this has been underappreciated. My background is a bit in high performance computing, so I want to emphasize this point. You have to be honest about it. What happens in an arcing process, there's a lot of stuff going on very short time scales, on very short length scales. So you typically need large meshes and very short time steps to get physically reasonable results. This is in fluid dynamics, this is not a problem anymore. Flow solvers are very well parallelized, and you can run them on hundreds or thousands of cores without problem. Electromagnetic simulations, if you use finite element methods, are a bit more difficult. They don't scale that well. And of course, the scaling, if you have a huge system, you want the coupling between the two codes to be fast. I would say that a really truly scalable code is not yet available. I would be delighted to work on such a project for a public domain code that could be developed by consortium, but we are not that far yet. Anyway, so what we have done, and I think we were many years ago after presentation I gave at the NAFEMS conference, we were approached by Star CCM. In those days, it wasn't yet Siemens, it was CJ Dapco. And they asked us whether we wanted to work with them on simulations of electrical arcs. And we have done so. We have implemented the appropriate equations in their tool. To me, it's simply by far the best tool available today for implementing these equations. It has allowed us to implement them with quite a little programming on our side. We basically do it build it on existing functionality that is in where. On this link, you can see an example of this of a simulation that we did for Siemens, or using this tool with a model breaker. And of course, we are very happy to to collaborate with people, because we are a bit in a different situation. We are at the university. Many of these simulations have been developed by corporations. We have a problem now a bit that we have a very nice simulation tool, but we have nothing to simulate because we are not developing circuit breakers on our own. And here you can see a bit the state of the art of our ARC simulations. The point is that such a simulation can today be set up with relative ease. It's not a big research work. We have a tool and most of the material models available, and setting up such a simulation for a device is a work of a couple of days, and then it should be running. Okay, so I want to start. Well, this is not a rant, but it's funny when I think back of the history. So when I was asked at ABB to look into this problem of ARC simulations, I think it was back in 2003, one of the first things I did, I went to a plasma, it was actually a software vendor, but it was a plasma simulation conference in the United States. I met Mark Kushner from University of Michigan, who is a quite known person in the ARC simulation field. And he immediately told me that he thought it was a very good idea and a very nice thing. And he told me that if your management agrees, you should start with simple experiments in argon, because in order to develop a good algorithm, you need to have as little unknowns as possible. Argon is a simple gas, and if you have a simple experiment, you could actually check that your simulation works. Then, of course, he added, needless to say, your management will not agree. And then we worked on this for many years at ABB. I remember also talking to Karl-Heinz Küfer. We had a collaboration with Fraunhofer Institute in Kaiserslautern, and he pointed out that one of the problems that we have in this business is that most university professors have solutions looking for problems and are not. It's difficult to collaborate because they typically want to continue doing what they did before and are sometimes a bit difficult to get involved in such industrial project. Anyway, so my bottom line is that there are simply projects also in the private sector where you really have to accept solving this problem takes 10 years, and it's better to look at this way than to start 5 2-year projects that all fail. I think there was a certain amount of frustration for my part working at ABB that we always start a new project that promised to solve a problem in 2 years, and they never did for some reason. Anyway, that's the end of my presentation. I think I'm still on time, so thank you so much for your attention, and I'm very happy to take your questions.
Thank you, Professor Nordborg. You are very good in time. And as I followed your work over the last years also closely, I can fully agree on what you presented, experienced partly on the own body or working
Exactly.
area.
Yeah, I think we know the feeling. It's fun that well, Rome wasn't built in one day. That's kind of a saying.
Yeah. So far, I cannot see questions from the audience so far, but there will probably come a lot of questions afterwards.
I'll see. There's some delay, I think, in this question too.
From my point of view, I would just add a comment. We hope that you will be heard by the software industry with your estimations or conclusions. And we are still curious what comes in this area. Do you have the feeling there's more than STARS ECM coming?
Well, that's a good question. I don't think it is a big focus on software vendors. I think STARS ECM was the only one that really decided to really implement something for that.
Questions are coming.
Okay.
Paul Slade, what about the Fluent software?
Well, the Fluent software is an excellent software for fluid dynamics. It is a bit outdated from the handling. Of course, I did use to work for ANSYS or for CAD-FEM, so I know it quite well. The interface it is a bit old-fashioned, and the coupling to an electromagnetic solver is a bit difficult. But I mean, that is, I think, tool number 2. If you look at, we also used to work with that. We fluent coupled with some electromagnetic solver. I think that is a standard approach in industry. Very many companies do that. And as I say, we did it too. But there is this. What we realized was that it takes quite a. At some point, you have a feeling that you spend more time on fixing software bugs than implementing physics, and that can be quite frustrating. One point is, of course, that in very many ARC applications, you need moving geometries. For example, you have contacts openings, you need remeshing, etc. And if you try to couple 2 different tools, and you have 2 separate meshes, and both the meshes have to be modified, it can get quite difficult.
Okay, we are out of time, unfortunately, and questions have been coming, so I asked questioners to directly talk to you.
Yeah, please send me questions. I'll be happy to comment.
Once again, thank you very much for that.
Okay, you're welcome. Thank you.
Okay, Hans. Herr Lindmeier war vorher gerade noch hier in der Backstage.
Gelesen, ja.
Und jetzt ist er auf einmal verschwunden.
So habe ich gerade nach Nordborg abgewürgt.
Okay. Vielleicht kannst du...
also ich bin noch da.
Ja, vielleicht können wir noch ein paar Fragen machen und schauen, ob er wieder reinkommt.
Ja, sind die Fragen noch da?
Ja. Fragen, bevor ich mit dem Video sonst starte. Danke.
Okay, we have lost the next presenter for a few minutes, so we have time to answer other questions. Christian Rümpler asked, what is the major bottleneck in the computation in your opinion?
Well, with the tool we have today, I think it's with the electromagnetic part when we have ferromagnetic materials, because the finite element solver. The advantage with the STAR CCM tool is that they actually have they have 2 electromagnetic solvers. One is implemented as a finite volume code, and that is very scalable and uses exactly the same mesh as the flow simulation. The electromagnetic finite element uses a different mesh, and of course is not so scalable. And that means that if we have to run with electromagnetic materials and ferromagnetic materials, and of course we do that for low voltage breakers, then that slows down the simulation significantly.
Another question, did you do comparisons with real tests?
Yes, we have actually had quite a lot. But of course, these have been collaborations with corporations, so we have there's not much we can show you, unfortunately. So therefore, again, if someone at the university, we would love to have more experimental data from that could actually be published, where we could also compare simulations with reality.
Another question, what difference do you see between STAR CCM and other software as Console, for example?
Well, that's a very good question. I haven't really looked into that. It probably is something one should look into again. We did evaluations at when I was at the ABB, but that's many years ago, of course. Generally, I think Console is an excellent tool, but it's not an extremely strong flow solver. It's not possible to run fast flow simulations on very many million elements with Console, because it uses a finite element method for everything. But I mean, again, I'm not. I have to confess that the last time we tested this was many years ago, and there might have been improvements since that then. And yeah, and one should probably look into it again.
Why do you suggest a 10-year project, although results are available in a few days?
Well, that was for the development. We now I think that this was sort of a learning, something we learned from the last years. I've been working on in this field for 10 years, for 20 years now, and I think now we have a solver that is good. I mean, I do think that the message from my presentation is that if you have a circuit breaker, be it low voltage or we can't, I don't think setting up a simulation for vacuum breaker would still be a challenge because the physics is different. But if it's in air or SF6, we would be ready to get your breaker simulated quite quickly. However, and this is of course, we also wouldn't expect the first simulation to agree perfectly with experimental results. There's always a significant amount of tuning and tweaking and trying to find the right proper material models, etc.
Okay, unfortunately we are not on hold of the next presenter. There was another question. Does your simulation tool enable to see the effect of opening speed and estimate the voltage?
Yes, so we do, what you get out of the simulation is, of course, we do always couple it to a circuit. So of course, we get current voltage characteristics. We can see when there is when the arc is extinguished. And for the opening speed, we have of course tried everything. We have tried with predefined opening speeds. We have also done simulations where we actually model the dynamics of a contact, also using the gas pressure and the electromagnetic forces acting on the contacts. And of course, that has makes a significant difference.
I think there's one last question coming in. Have you ever tried to simulate electrical damages by an arc?
Not directly. We actually had a request for that, but the project never materialized. So what we have done, and there is we had a collaboration with ETH where we have simulated ablation. So it depends on which damage you want to look at. We have done simulations of ablations, modeling of ablation, but mainly to get the proper pressure build-up. We have not really modified the geometry. What you should do is, of course, to then, when you have ablation in a PTFE nozzle, for example, in a high voltage breaker, you would want to modify the contour of the nozzle because of that. We haven't done that. Yeah, I think it would be doable. It wouldn't be the easy. Yeah, it wouldn't be. It would be quite time consuming, but it would be possible. And of course, then I'm a big promoter. Perhaps I should have put that as my standard or the last statement. You always have to look at exactly which problem you want to. You don't do simulations to simulate the breaker. You typically want to answer very specific questions, and the question in this case would be: is this damage really the main point we want to look into? But yes, I think we could do it. We haven't done it so far.
Okay.
Okay.
I'm informed that Professor Lindmeier is approaching us.
Okay, so sorry. So I stole some of his time. I have to apologize for him.
We tried to use it for answering questions. I think that was as good.
Okay, thanks a lot.
For the community. And once again, thank you very much.
Okay.
Yeah,